Hello everyone. In this final video, we're going to take a look at a couple examples involving moment generating functions and a couple examples involving transformations of variables. So our quick overview is in one, we'll construct the moment generating function for the exponential random variable, then look at some follow-up questions. In example 3, we'll take a look at a transformation of one variable. Fairly straightforward, easy example. But in 4, we look at another transformation of one variable that is a moderate problem, a little bit more difficult than the first one. So, suppose x is an exponential random variable with parameter lambda. Then find the moment generating function for x. All right, so we begin by thinking about the definition. So the generating function is defined to be e of t of x, and this would be the integral of e to the tx times our PDF for x. So in the case of an exponential, this PDF looks like lambda times e to the minus lambda x dx. We need to find this integral with respect to x. So before going any farther, we can simplify to a degree here by using the property of exponents that tells us when we have the same base, we add exponents. So this becomes lambda times e. We factor out an x, so e to the power t minus lambda x dx. Now this integral is much more manageable, so we could evaluate the integral. We end up with lambda over t minus lambda times e to the t minus x, where x goes from 0 to infinity. And keep in mind that when we do this, we assume t is less than lambda. So since t is less than lambda, this term up here is negative. So when we substitute in the infinity limit, this term will go to 0. When we substitute in the x equals 0 limit, this becomes e to the 0, which is just 1. And we're left with lambda over lambda minus t for t less than lambda. So this is the MGF, the moment generating function, when x is an exponential random variable. Now from this, we can do various things. For example, we could determine the expectation of x, the variance of x. These functions, they may seem a little unusual, but they turn out to be very useful in a lot of theoretical explanations. So here in the follow-up example, let's use the moment generating function to verify that if x is exponential with parameter lambda, we have its mean is 1 over lambda. E to the x squared, this is sometimes called the second moment, is 2 over lambda squared. The variance, 1 over lambda squared. And let's give a definition of moments. So for part A, we want to find e of x. So what we have to find is the first moment, which requires that we take a derivative with respect to t. So this derivative becomes lambda over lambda minus t squared. You could do this just by applying our quotient rule. And then we have to evaluate at t equals 0. So you could say that this simplifies, the t drops out. We get lambda over lambda squared. Canceling out a lambda, we end up with 1 over lambda. So that's our well-known formula for the mean of an exponential RV. In part B, we find the second moment, which requires the second derivative with respect to t. So we can go back here, take the derivative of this first moment, if you want. We end up with 2 lambda over lambda minus t cubed. Again, we have to evaluate this at t equals 0. So we get e of x squared is equal to 2 over lambda squared. Now we could put a and b together and easily see that the variance for our random variable x, right? We use this shortcut formula, e to the x squared minus e to the x, so quantity squared. I substitute in, and you could see that this will be 2 over lambda squared minus 1 over lambda squared, which will leave us with 1 over lambda squared. Finally, we defined the term a moment. So e of x to the n is the nth moment obtained by taking the nth derivative of the moment generating function and setting t equal to 0. Okay, so that completes examples 1 and 2. Now let's take a look at example 3. Suppose Jack calls his girlfriend Rose every day on his cell phone. Anybody recognize Jack and Rose? The time x in hours that they talk is uniformly distributed between 0 and 2. Jack pays $2 per hour on the phone plus $5 per day. So we have our transformation here. We think of y is equal to 2x plus 5. That's the amount his bill is per day. Questions are, find the probability he spends more than $6 for a given day. Find the expected amount that he spends on a given day, and find the standard deviation of the amount that he spends on a given day. Now, I suggest that you stop the video and try this. You should find that after doing maybe a little bit of work, this is quite a manageable problem. Okay, first thing to observe is that y will be uniform on the interval 5, 9, right? We knew x was uniform on 0, 2, but y is equal to 2x plus 5. So from that, you can infer that y will be uniform, and that gives you another way to solve some of these problems. So if we think in terms of calculating integrals to find this, we know that the PDF for y will be 1/4. It's going to be 1 over the length of this integral, right? That's how we get a PDF for a uniform. So we could find the probability y is greater than 6 by looking at this easy integral. Integrate from 6 to 9, 1/4 dy, be 9 minus 6 over 4. This gives us 3/4 or 0.75. For part B, we want the expectation of y. Well, if I use the fact that y is uniform over 5, 9, it's really the midpoint of this interval. So I get 5 plus 9 over 2, which is 7. Or we can sort of go back and focus on the transformation. E of y, we know y is 2x plus 5. Using properties of expectation, this becomes 2 times e of x plus 5. X is uniform from 0 to 2, so e of x is 1. So this becomes 2 times 1 plus 5, which is 7. So this just gives us a second way of finding E of y. In part C, we're asked to find the standard deviation of y. So we could use our formula. All right, here's a formula to find the standard deviation of a uniform random variable in general. Square root b minus a squared over 12 for the standard deviation. So here we would be looking at, now this should be 9 minus 5 squared over 12. We have 4 here. Must have been thinking of the results because 9 minus 5 is 4. So we would get 4 squared over 12. And then we have to take the square root of that. We end up with 1.1547. Or we can go back and focus more on the transformation. Sigma of y is equal to sigma 2x plus 5. So when we're taking standard deviation, this becomes 2 times sigma of x. And we end up with 2 times the square root, 2 squared over 12, which gives us 1.1547. Okay, so that completes example 3. Now for example 4. Back to cheeseburgers. Let's suppose Sally owns a burger restaurant and the cost of a pound of beef is $3.75. So she sells cheeseburgers, but we'll just call them burgers for short. And the cheeseburgers, they're approximately quarter pounders. They contain an amount of beef that's uniformly distributed between 0.23 and 0.27 pounds. Now, on each of her burgers, she includes a slice of cheese, and the cost there is 35 cents, and the bun, which costs 33 cents. Let's say burgers are listed on the dollar menu and sell for $1.60. Assuming the only cost of making the burger are the beef, the cheese, and the bun, what's the probability that the costs exceed the price of the burger? Okay, so we'll start off with the cost of a burger, and here we have 3.75x plus 0.68. So that's our transformation. X is a uniform random variable between 0.23 and 0.27. This, remember, we get from the cost of a slice of cheese plus the cost of the bun. So 0.33 plus 0.35 gives us 0.68. Next step, let's try to think about her break-even point. So she sells the burgers for $1.60, but we have to sort of subtract off cost of the cheese, cost of the bun. So 0.92 is critical. We could say that when the meat costs more than 92 cents, she's losing money. So we need to figure out what 92 cents is in terms of the amount of meat, right? If we think of 0.92 over 3.75, okay, that's 0.245. Okay, so this would, now let's think of this as pounds of meat in the burger, and we know that we need to find the probability X is 0.245. So when we find the probability that X is greater here, then she'll be losing money. Okay. Well, this is something we can do. Since X is uniform between 0.23 and 0.27, the probability X greater than 0.245 is equal to 0.27 minus 0.245 over 0.004. Okay. So there may be a couple of different ways to get to this point. If we once again think in terms of an integral, right, the PDF for x would be 1 over 0.04, and we would be evaluating an integral here. This would be our lower limits. 0.27 would be the upper limit. So the result of the integral would be something like this. And when we take this another step and simplify, we end up with the probability of 0.625. So that's it. We've reached the end. I hope you've enjoyed the videos.